Hello and welcome back, everybody. Today in geometry, we will be looking at the second to the last section of chapter 9, which is going to be looking at a specific type of triangle, more specifically a right triangle, where the angles are 30 degrees, 60 degrees, and 90 degrees. And in the future, we will definitely be focusing a lot on this type of triangle. So we want to kind of just kind of delve in it a little bit, see what we can do in terms of scratching the surface to see if there's any kind of special characteristics that we can extract from it. Okay. So let's go ahead and start on this. The first thing is we're going to look at this theorem right here, which is theorem 9-26. So unfortunately, it doesn't have a name, but it's actually very useful. And I'm not quite sure where, well, I don't know. Maybe it's just up to the author. But anyhow, here's what it says. The median to the hypotenuse is supposed to be 1/2 as long as the hypotenuse. So in this triangle over here on the right hand side, the first thing you should recognize is that it's a right triangle because they're referring to the word hypotenuse. And what I want to do is I want to prove that the median, which is located right here, dB, that is going to be half the length of the hypotenuse. So that is to say, I want to prove, or I want to show the following. I need to show that dB is equal to 1/2 of AC. All right, so I wrote the proof underneath. So let's go ahead and see if we can mark everything up so you can understand where it's all coming from, okay? So first things first, what I need to do is, and let me go ahead and choose a different color. Maybe this will look a little bit better. First, I'm going to introduce a point E such that EC is equal to AB and EA is equal to CB. Now, in terms of where that location is, let me go ahead and draw it for you, okay? So this point E that I'm looking for is actually located right here, okay? And it's such that EC, here is the segment EC right here. I want it to be specifically equal to AB. So you can see that this part right here is going to be equal to this part, okay? Now, in addition to that, EA is equal to CB. So going to the right, you can see that this part right here, I want that length to be specifically equal to this length. Now, looking at what we have for that equilateral triangle, oh, sorry, not equilateral triangle, for that quadrilateral ABCE, you'll notice that the opposite sides are congruent to each other. And there is a theorem, if you go back a little bit, which says that, hey, by the converse of the theorem apple, and I really should give it a better name for it, quadrilateral ABCE is supposed to be a parallelogram because the theorem says that if you have a parallelogram, if you have a quadrilateral where both of the pairs of opposite sides are congruent to each other, then that quadrilateral is a parallelogram. That's what that theorem says. So then, so far right here, we have a parallelogram, which we can kind of work off of. So the next part now says that by theorem 9-23, which now says that, hey, now that we have a parallelogram, that contains a right angle, then that means that it's a rectangle. So that was a theorem from the previous section, which once again states that if you have a quadrilateral, which is a parallelogram, and if you have one right angle, which we do because this is B right here, then that means the rest of it is going to be right angles as well. So that basically tells me that it's going to be a rectangle as a conclusion. So as of right now, let me go ahead and fill in those pictures or fill in those knowns or the stuff that we've proven so far. ABCE is going to be a parallelogram. And now more specifically, these are right angles because we snuck one in there. And by that theorem, then that means that we have 4 right angles. Well, now that we know that ABCE is a rectangle, then what I can do is continue by finishing off this length right here, ED, and then B right here, okay? Because if you look at it carefully, that means that EB is a diagonal of the rectangle, just as AC is also going to be the diagonal of that same rectangle. And since it's a rectangle, then those two diagonals should be congruent to each other. That was something that we proved a while back. So the next part says that because if you have a rectangle, the diagonals are going to be congruent to each other. Then by theorem 9-18, then we can say that EB is and CA bisect each other at point D. Going back to, again, that theorem a while back that says that if you have your parallelograms, then the diagonals are going to bisect each other. And since they're equal to each other to begin with, then that means that ED is going to be congruent to DA, which is congruent to DB, which is then congruent to DC. And right there, if I just kind of cut off the part that I don't need, but you can kind of see now that DB is definitely equal to 1/2 of AC then, okay? All right, so now let's go ahead and move on to the next one to be a little bit more specific. Now let's go ahead and delve into that 30, 60, and 90 triangle that we were talking about. So here for this theorem, it says that if you actually have a 30, 90, 60 triangle, the shorter leg, which is supposedly the side that is opposite of the 30-degree angle, because that's the smallest angle according to chapter 7, is supposed to be half the hypotenuse. So in this picture on the right-hand side, what is it that I need to do is I need to show that AB, which is the shorter side, is supposed to be equal to half the hypotenuse. Then that means it's AC. So let's go ahead and hit into this one. What I would think is we probably need to use that previous theorem in order to prove this one. So my guess is that let's go ahead and introduce that point D, which is the midpoint of the hypotenuse. So over here, we're going to go ahead and draw point D. So that is going to be our first part. Introduce point D, which is the midpoint of AC. Then by the previous theorem, not 927, but rather 926, then what we can say is that the three lengths over here, DA, DC, and also DB, which I'm about to draw right here, then those three right there are going to be all congruent to each other then, because of what we just did. Okay, because if you remember, DB is supposed to be half of the hypotenuse then, okay? All right, let's see. Let's go ahead and do a little bit of digging back. Look at the triangle that's over here, okay? Look at the triangle that is formed in this part, DBC, okay? Because we just said that this side is congruent to this side, then by the isosceles triangle theorem, that was a long time ago, then that means that this guy has to also be equal to 30 degrees. So that's the next part. By ITT, the measurement of DBC is equal to 30 degrees. And doing a little bit of math and just using like complementary, we can say that DBA, the angle next to it, has to be 60 degrees as well. So over here, I can go ahead and sneak in a 60 degrees because if you look at this part, there's supposed to be a right angle there. And finally, now let's go ahead and focus on the other triangle over here, which is supposed to be ADB, okay? If one of the angle is 60, the other angle is 60, then the conclusion is that this last angle, ADB over here, must also equal to 60 degrees because if you remember, the sum of all of the interior angles in a triangle has to be equal to 180. So 180 minus 60 is equal to 60. And hey, lo and behold, what do we have here? We have a triangle that is going to be equal angular. So going back to my proof right here, since the sum of all the interior equals to 180, then that means the angle is equal to 60. And there, because all the angles are the same, this is supposed to be equal angular, which also states that it's supposed to be equilateral triangle. So in conclusion, then that means DB, which has a single mark, is going to be congruent to DA, which has a single mark, which we had earlier. But now more importantly, AB also has a single mark because of that equilateral triangle. So the last conclusion is that by definition of equilateral triangle, AD is equal to BC, and also that's equal to AB. Okay, so there it is. So that is the special characteristic of a 30, 60, 90 triangle. The shortest leg is also going to be equal to half of the hypotenuse. Okay. All right, now let's look at the last part, which is the converse of that. So meaning this time around, let's say that still once again, we have a right triangle. And what I'm telling you is that this guy over here is going to be half the length of the hypotenuse. So I guess if I can call this A over here, then that means that this is equal to 2A. So given that that's true, right? If the shortest leg of a right triangle is half the hypotenuse, then I need to prove that you have a 30, 60, 90 triangle then. So I need to show that this guy right here and this guy right here, one of them is 30, the other one is 60. All right, so let's go ahead and do this then. Well, we've been digging into the midpoint of the hypotenuse every single time, so I feel like that's also a good place to always start. Let's go ahead and call that D over here, okay? Now, for this one, I'm not going to write up the proof because I feel like this one we can probably do algebraically and probably orally just to make it a little bit easier. Here, let's go ahead and do this. If you recall earlier, we said that AC is supposed to be equal to 2A because if you remember, A is supposed to be the length of AB over here. So let me just go ahead and write this a little bit better. We know that this is A, so therefore the hypotenuse is equal to 2A according to the given. Now, that tells me that DC is going to be equal to A, and then also DA is going to be equal to A. And I'm going to go ahead and draw the median just as we've been doing so far. Okay, looking at the sides, I can see that this right here is congruent to this right here. And so what that means is the following angles are going to be the same. Let me go ahead and call this angle Y right here, and let me go ahead and call this angle Y because of isosceles triangle theorem. All right, so far it looks so good. Let's see, what else do we have to work with? How about the bottom part, okay? If you remember now, going to 9-26, the very first theorem that we just proved in this section, we can say that the median of the median to the hypotenuse is supposed to be equal to one half of the hypotenuse. So that means that this guy right here is supposed to be the same thing as this guy right here, which is the same thing as this guy right here. So then that means that once again, we have our equilateral triangle. So that means that this guy right here must also be equal to Y. Well, judging by what we have right there, then in that triangle that we just looked at, this triangle over here, ADB, the sum of the interior angles is equal to 180 degrees. So Y plus Y plus Y is equal to 180. So 3Y is equal to 180. So therefore Y is equal to 60. And as soon as we discover that this guy is equal to 60, and if you remember, angle B is a right angle, so that's going to be 90 degrees. Then looking at the entire triangle over here, this guy right here must equal to 30 degrees because 30 plus 60 plus 90 is equal to 180. Well, there you go. Thank you so much for watching. Hopefully this one was insightful and you learned something from it. I will see you next time. Talk to you later. Bye.